Greetings, my name is Hugo Oliveira, and I'm currently a postdoctoral researcher at the University of São Paulo. My PhD dissertation was done at Universidade Federal de Minas Gerais with professors Jefferson dos Santos and Arnaldo Albuquerque as advisors. This presentation will summarize the main points of the dissertation entitled Semantic Segmentation with Multi-Source Domain Adaptation for Radiological Images. One of the main applications of machine learning in medical imaging is the automatic delineation of organ masks, also called organ segmentation. The most common types of learning models are the supervised ones. These models, however, often fail to generalize to new data. Supervised models are also unable to learn from unlabeled data. During this talk, we will investigate some ways of circumventing these limitations. The body of knowledge that aims to compensate for the inherent domain shifts in real-world data is called domain adaptation, or DA. DA between a pair of domains, source, denoted by S, and target, denoted by D, can be unsupervised, semi-supervised, or fully supervised, depending on the label availability of the target datasets. Despite finding success in multiple applications, domain adaptation usually operates only on a pair of datasets. This strategy is suboptimal in domains with multiple data sources, though. Hence, the central question of this research. Could it be possible to leverage multiple data domains at once to improve the generalization of domain adaptation algorithms? We will find that this domain generalization is possible with the aid of some state-of-the-art methods in deep learning. We will build our knowledge starting from the simpler case of supervised semantic segmentation. The network architecture shown in the slide is a very common one for segmentation of medical images, called the UNet. This architecture is the one used for all supervised learning in this work. UNets are also the backbones of many image translation architectures. Image translation from unpaired images from two domains A and B can be achieved using a concept called cycle consistency. In a neural network architectural sense, this can be achieved using the pipeline shown in this slide. Notice that this is a generative adversarial network, again, composed of two discriminators, DA and DB, and two generators, GAB and GBA. Multiple methods follow basically the same pipeline shown earlier. However, prior to 2018, none of them leveraged this knowledge for domain adaptation in semantic segmentation settings. In this context, we proposed our domain-to-domain, called D2D, approach for dense labeling DA at SIBGRAPI 2018. The following session will be devoted to present D2D. We start from a very similar architecture to the one presented for unpaired image translation, with the addition of semantic masks, denoted by YS, in the source domain. This additional supervision allows us to plug a segmentation model, for instance a UNet, at one end of the network. This model, MT, uses the labels from the source domain and synthetic data from the target domain. In other words, MT compensates for the domain shift between domains S and T using image translation. The same strategy can also work on a semi-supervised setting when there are some labels YT for the target domain. We used only two chest X-ray datasets to test D2D in 3 tasks: lung, heart, and clavicle segmentation. These are the Jacquard results for these experiments in different regimes of target supervision. When there are enough labels from the target domains, D2D behaves indistinguishably from fine-tuning and from scratch training on the target dataset. However, in label-scarce scenarios, D2D already presents significantly better results than baselines. At last, in the unsupervised domain adaptation case, D2D outperforms pre-training on the source dataset by a huge margin. We also present some qualitative segmentations resulting from unsupervised DA experiments, including failure cases on the last column. Pairwise DA, however, has serious limitations for domain generalization. Up until 2019, image translation for domain adaptation was solely pairwise. This trend can be seen in this table containing most of the related work to this research. In order to bridge the gap between multi-source image translation and domain adaptation for segmentation, we proposed the conditional domain adaptation GANs, called the GANs. While pairwise DA operates using two specialized generators, GST and GTS, and one supervised model, MT, we proposed one single conditional generator capable of translating between any input domain and one isomorphic domain, denoted by the cursive I. From I, we can train one single supervised model M that is able to segment samples from any source domain, be it supervised or unsupervised. On the slide, you can see the base architecture of the GANs, composed of only one generator divided into an encoder, GE, and a decoder, GD, one single discriminator, D, and the supervised model M, that receives the embedding of the isomorphic space. For scalability, the training is always conducted in a pairwise fashion, with randomly drawn datasets at each iteration. In this case, the labeled dataset A and the unlabeled dataset Z. Aiming to merge the unsupervised learning of image translation with the supervised learning of segmentation networks as UNets, we use a composite loss function for codagons. Our loss contains two cycle consistency terms for enforcing good low-frequency component reconstructions after translations, two adversarial components for improving the high-frequency aspects of the translated images, and up to 4 supervised components applied to the labeled samples encoded into the isomorphic space. In order to test the generalization capabilities and scalability of codagons, we tested 3 radiological domains: chest X-rays, or CXRs, mammographic X-rays, or MXRs, and dental X-rays, or DXRs. 3 tests were available in CXR datasets: lungs, heart, and clavicles. 2 structures were annotated in the MXRs: pectoral muscles and breast region. At last, the XR datasets had labels for mandibles and teeth. In total, there were 8 CXR datasets, 6 MXR datasets, and 2 DXR datasets. First, we will present the results of semi-supervised DA in partially annotated datasets, beginning with CXRs. While WTD and pre-trained UNets were severely unstable in scarcely labeled target dataset regimes, codagons, presented in red bars, performed well, even in the total absence of labeled from the target. A similar trend can be seen for MXR target datasets, now clearly evidencing that codagons are also able to improve with more labels from the target. This adaptability to distinct label scenarios on the target domain was observed in most experiments with codagons. Now, we show some visual segmentation results of pre-trained UNets, domain to domain, and codagons. First for the 8 CXR datasets on lung segmentation, and then for heart and clavicle segmentation. Visual results in MXR datasets were similarly favorable to codagons. At last, on the DXR datasets, the comparison of codagons and D2D was inconclusive, because there was only a pair of domains involved in the training procedure. In this case, the lack of data diversity limited the performance of codagons. The last set of experiments focused on synthetic 2D data computed from 2D volumes. We start with an unlabeled 3D CT scan dataset and extract 2D projections of this data with average and maximum intensity projections. These 2D projections serve as source data and bound labels for CXR datasets. We then apply codagons to extract the lung masks for the 2D projections using the labels from real CXR data as source. The binary end operation between bone masks and lung masks in the 2D projections can be used as noisy labels for rib segmentation. The second codagon is trained using these noisy rib masks as label sources, resulting in a model capable of segmenting ribs in any CXR dataset without requiring a single labeled image. For these experiments, we use the LIDC dataset as source for the 3D data and 7 CXR datasets as targets. In this slide, we present the ROC and qualitative results of codagons and pre-trained networks in rib segmentation. We can clearly see the gap between the proposed method and the baseline on the ROC curve, while the qualitative results evidence the complete lack of generalization capability of simply using pre-trained UNets in unsupervised DA scenarios. In this work, we observed the feasibility of employing image translation to improve medical image segmentation generalization in deep neural networks. Conditional DA proved to be very effective in generalizing from even one single source dataset to multiple target datasets, even in fully unsupervised DA settings. Codagons can then effectively be used to achieve domain generalization in medical image segmentation, while also being highly scalable to a large number of target domains. The generalization capabilities of codagons also allow for cross-modal translations between image modalities, even when the labels are synthetic and noisy. The original research that resulted in codagons branched into several directions, serving as a base for multiple PhD, master's, and undergraduate works. Current improvements to codagons include the use of data with different dimensionality, such as volumetric medical imaging, employing modern image translation architectures that encourage multimodal modeling in the isomorphic space, and even performing zero and few-shot learning on novel domains. This PhD work resulted in multiple publications directly related to this research, including journals and conference papers. The authors would like to thank NVIDIA for the donation of the GPUs, and CAPES, CNPq, and FAPEMIG for the financial support provided for this research project. Thank you very much for the attention, and please feel free to check out the official implementation of codagons, the PhD dissertation, and other related papers in our research group using the following QR code.